Hello, everyone. This is Michael E. Yeaman with another Geology of Sculpting Stone. Today, we'll be talking about Montana Quartzite. And as always, we ask ourselves, why should we care about the geology of our stone? Well, stone sculpture is one of the few art forms that date back to the very beginning of recorded history. And the story of stone is unique. Therefore, knowing more about the geology of your stone will allow you as stone sculptors to select specific stone types that for you have a compelling history and maybe are of interest to your viewer. You can also then marvel as you're working the stone about its various elements of color, texture, and composition. You can consider how your sculpture's chosen artistic form relates to the science of the stone. And finally, you can weave that story, that geologic story, into the final artwork, which might enhance the interest in your work for both yourself and for potential buyers. And as usual for all of the Geology of Sculpting Stone series, we have a three-part outline. We'll begin by taking a look at the stone defined, its general description, physical and chemical properties, and historic use. We'll take a look at specimens, pictures, both large and small scale, thin sections. We'll take a look at specifically where you can find this stone. Then we'll delve a bit into the geology, its age and description, the formation process and the environment for the stone, the global geographic, paleogeographic setting, where in the world was this formed and at what time, and then we'll take a look and see if there's any modern analogs of where the stone type might be forming today. Finally, we'll close out with taking a look at select creations, both in art and architecture. So let's begin by having a general description, physical and chemical properties, and historic use of quartzite. Quartzite is a metamorphic rock made from sandstone. Its name is derived from its compositional makeup, often 100% quartz or silica dioxide, also simply referred to as silica. When a sandstone is buried and heated up, it can fuse into a hard, equal grain-sized rock, which we call quartzite. Quartzite, especially on a freshly fractured surface, has a sugary texture, a glassy luster, with a tendency to fracture in planes, often along the old sandstone bedding surfaces, a characteristic of many quartzites. Quartzite color is often white to beige, but frankly can come in a wide variety of colors due to minor impurities that may have been in the original sandstone and or were incorporated when the quartzite was metamorphosed. Quartzite has been used for a long time. Because of its durability, it was used as Stone Age tools, although less common than more easily worked flint and obsidian. It was a source of silica for metallurgical purposes, and it was used in manufacturing of brick, aggregate and construction, and roadside industries, armor for seawalls. In fact, it's a very preferred stone in the construction and roadside business today. And occasionally it was used as dimension stone for building, facing, paving, countertops, etc. We'll talk more about all of its many faceted uses here as we go along. So let's take a look at some specimens. Let's begin with the macro, big scale. Here we see on the upper left outcrop. You can see a little bit of hint of some of the maybe old sandstone bedding planes that are still seen in the metamorphosed quartzite. On the upper right, you can see a weathered boulder with some of maybe the preferred sandstone bedding planes on the upper surface. And as we zoom on in, we can see some freshly broken pieces with the beige to off-white, in this case, a variety of different weathering characteristics, especially on some of the pieces of the lower left rock that have been exposed to rain and weathering conditions over the years. And then finally, on the lower right, if we zoom in on a hand specimen, we can see some of that sugary texture we are describing that you oftentimes see on a fresh face of broken quartzite. Well, if we take a look at thin sections and remind ourselves that a thin section is simply just a thin slice of rock which we can shine light through, in this case, just 2 times magnification, we can see on the upper left the nature of a quartzite, and as I mentioned before, the fusing together, the interlocking of the quartz grains as the deposition under pressure and temperature has actually molded the sandstone from a layered loosely aggregated block of sand grains into a fused interlocking series of quartz grains that you can see in this thin section. And then finally, when you see a quartzite go underneath some pressure, as it's been converted from sandstone into quartzite, sometimes the compression direction of that pressure is seen by the alignment or stressing of the fused quartz grains. Here we see a picture where the compression looks like it was diagonal across the slide, with the arrows implying the probable compression and flattening texture being applied to this quartzite. Quite intriguing, these little thin sections, I think. All right, well, where was quartzite located, or where is quartzite located today, and where can we find it besides our spot here in Montana? Well, quartzite is widely occurring, especially in ages where many mountain ranges had formed and are present either in current mountain range areas today or ancient mountain range areas. You can see on the left where I've outlined some of the more major mountain ranges present today. And in almost all of these places, you can find quartzite having formed within a few million years of the formation of the mountain ranges itself, because of the pressure and temperature the buried sandstone has gone through. And as I mentioned, it's not just present day mountain ranges, it's areas around old continental cores, which oftentimes have paleo mountain ranges that were left behind, here shown in the darker color on the right slide, where some of the old areas like the Beartooth, the Slave Lake area, Lake Superior in the North American Craton. This zone, which we describe as a craton, is oftentimes just the core element of ancient crust where over time they've amalgamated to form our present day continents. But here are some of the major cratons. There's the South American one. There's some very old ones in Africa, including some south in the South African area itself. There's several old ones in the Siberian area here to the upper right. And India, through a good deal of the Indian southern craton, is containing some old mountain ranges. And in Australia, which itself is made up of a lot of old continental material, the area around Jack Hills in Western Australia is really one of the more fascinating areas. We find some extremely old rock, including ancient continental cores, where they went through a process of burying sandstone and heating it up and forming the quartzite, which we're talking about today. But let's zoom in specifically on our area of Montana quartzite. So here we are now with a picture on the left of an area we call the Belt Basin. It's an old depositional area, many hundreds of millions of years old. It extends all the way from southern British Columbia all the way down into Idaho, with a good deal of it lying in northern Idaho and western northwestern Montana. It makes up, when it's been uplifted, some of the more unbelievably impressive mountain ranges in the Glacier National Park area. I've showed a couple of slides here where you can see East Glacier National Park in an area called White Sulphur Springs down here towards the southern end of the Belt Basin. You can see here very dramatically in this East Glacier National Park picture the layers of sandstone that are still present in this quartzite, still being preserved as very distinct layers, even though it's no longer sandstone, but it's been pressured and increased in temperatures to form the fused grains we are looking at in that thin section a little while ago. And then the Sulphur Springs deposit is a little bit more weathered, but you can still barely make out, I think, particularly on the lower section here, these layers of paleo sandstone that were the original form of the quartzite before pressure and temperature. So if we zoom in specifically about where we got our Montana quartzite, one thing I want to point out is that quartzite, although it's a widespread material, is not commonly worked by the Northwest Stone Sculptors Association, because Washington State and most of Western British Columbia does not include a lot of quartzite that's actively mined today. However, Montana produces a great deal of quartzite, and Carl Nelson, a couple of years ago, among others, discovered a very nice quarry, easily accessible, and brought back quite a bit of Montana quartzite recently, which many of us have chosen to work. So let's spend some time talking about this specific occurrence and locale. And it's in a place called the Macquarie Quarry. How about that? The Macquarie Quarry in Clinton, Montana, in an area that we just looked at a moment ago, the Belt Basin area. And what I've done here is some of the pictures that Carl took when he had a most recent visit. And I've zoomed in on a couple of spots. And here you can see one of these big front end loaders down here actively quarrying in the Macquarie Quarry. And here I've zoomed in on one area where you can see there is a distinct break across the Macquarie where you see a couple of different lines, a bit hint of slightly dipping beds below something we would call this sharp break and unconformity, and then maybe more linear units lying above it. And then over on the bottom right, some of the fractured quartzite that exists in the Macquarie area, and an old character up here working the quarry actively and bringing a couple of big blocks, maybe even one that we brought back to our most recent Pilgrim Firs endeavor here in Washington State last couple of years. Anyway, the Macquarie Quarry and the Clinton, Montana area has been a big source of this Montana quartzite for many years. So let's now spend a little bit of time specifically on the geology of the Montana quartzite. And so let's begin, like we always do, with taking a look at the age of the quartzite, of the stone, of our geology of sculpting stone, the Montana quartzite. And as I mentioned, it's part of this Belt Basin area. And in fact, this Belt Basin area is an extremely famous area from a number of ways geologically, here located in western Montana and northern Idaho. And it's particularly famous because it's quite old, but it maintains nearly a 25,000 foot section of sedimentary rock that was deposited roughly between, and here I'll show this here by highlighting it, from about 1.5 billion years ago to about 1.4 billion years ago. So, only over the space of about 100 million years, which geologically actually is a fairly short period of time. But over this period of time, this nearly 25,000 feet or more of sedimentary section was deposited, and it was made up of a series of rock types here, as I've listed here: sand and silt, various types of argillite, a type of a rock that contains both sand of various grain sizes. Here we have our fine grain laminated quartzite, and some coarse and medium grain quartzite, and then a couple of lower layers that contain some carbonates and some carbonate bearing types of mixed clastics or other types of sedimentary rock. And what I want to focus in here now is in this medium to coarse grain quartzite that we talked about just a second ago. And you can see now that near the top of the overall Belt Basin supergroup, there's a section of it called the Bonner Formation. So the Bonner Formation, as you remember, just a way geologists have a tendency to break rock types down into characteristics that they have in common. So because most of this area we call the Bonner Formation is medium to coarse grain quartzite, it's been grouped as a distinct formation name. And it is the majority of rock type that sits in the Macquarie quartzite area. So it is a very distinctive rock, as we saw in previous slides. And as I mentioned, the overall section is unbelievably thick, particularly in the Missoula area, and represents an old sedimentary basin 1.5 billion years ago that was having a great deal of sediment and sometimes some carbonate form in it. Well, let's zoom in now on a couple of pictures of rock outcrops of the Bonner group. And as I mentioned, the Belt Basin is this remarkably thick sequence of clastic, sand and shale, and some carbonate. And as I mentioned during the process, since its deposition 1.5 billion years ago, it's been buried and compressed. The lower slide is a zoom in on some of the elements of the Bonner Formation. As I mentioned, a medium to coarse grain sandy unit that's been converted into a quartzite. Feldspathic simply means it has quite a bit of feldspar within it, and it contains some elements of mica, which is that flat element of igneous rock. This can be both black biotite and white muscovite. And specifically want to point out here, one, we have this little Swiss Army knife for scale, but I want to point out, if you look carefully, you can see the little micro characteristics of the sand beds. We call these foreset beds. And you can see how they kind of curve, and they curve more tightly upward than flatten out. This is the original deposition of the sand as it was being deposited here in this individual little layer, not more than an inch or two thick, that makes up a great deal of the Montana quartzite. So in other words, in this slide, you see a 1.5 billion year old clastic sandstone that's been buried and warmed up to create the Bonner quartzite. And still, even after all that time and burial and temperature increases and fusing of the grains together, you can still make out some of the original sedimentary characteristics, just like you could see on a modern day sandy beach if you were to walk out to ocean shores in Washington State. And let's spend a little bit of time talking about its conversion process, how our sand becomes a quartzite. And so what I put here now is this very simplified model of what we call metamorphic grades. Now, by metamorphic grade, what I really mean is, as a rock, any particular rock is buried, warmed up, and increased pressure put upon it, depending upon what the original rock was, it will go through a series of changes as it has more pressure and more temperature applied. Now, with sandstone, which it begins as the parent rock of our Montana quartzite, initially sandstone will go through a grade or a description of a type of metamorphic characteristic, which we call a green schist facies. And by facies, we just mean a common characteristic or set of properties of the rock. Now, if that rock gets buried more and more deeply and additional temperature applied, it goes into an amphibolitic stage or facies. And finally, if it gets extremely high pressure and temperatures, it moves into a granulite facies. Now, because the pressure on the individual sand and the silica, as well as some of the other minor components that will be in your sandstone, you can actually use minerals to tell you what facies you're in that will form in different characteristics, where it be chlorite, epidote, amphibole, garnet, or pyroxenes. Now, our Bonner formation is sitting in kind of an intermediate stage of metamorphic grade, not super hot and super high pressure, but fairly pressured and reasonably warmed up. And so here I've mapped the Bonner formation as sitting somewhere between a low grade to intermediate grade facies. And as I've shown here down in the bottom, we just talked about in general that you go from sand to sandstone to quartzite, and sure enough, that's exactly what we see. And the Bonner formation, just to point out once again, is a quartzite where the sand grains have been fused together and produces this distinctive looking rock with the kind of sugary texture on its outer surface. Now, if we step back for a minute and talk about where the Bonner quartzite and how the Bonner quartzite might have formed, we have to go back and revisit our old friend plate tectonics. So once again, we have this common plate tectonics overview slide I put in many of my Geology of Sculpting Stone presentations, and it just allows you to take a look at the major types of processes that occur in plate tectonics in a cross-sectional view. And although this is not a presentation about plate tectonics, we're going to spend just a little bit of time talking about where and what type of an environment the Bonner quartzite might have formed in. So here, as you know, with plate tectonics, you have a spreading center developed with thin plates that are usually oceanic in this area, and it spreads away from the oceanic center. Some of the oceanic plates will subduct or dive beneath other plates on the Earth's surface, this one being a continental plate. They will melt. Some material on top of the subducting plate will melt and bubble to the surface as volcanoes. and form other deposits like granite down below the volcanoes. Some will be island arcs in the middle of the ocean. Some will be on big continental masses like North America. Now, the Bonner quartzite was deposited in a rather unique little place here, and I'm going to show it here as over here on the far right, something called a continental rift zone. So what can happen is not only do you get a compression occurring along continental margins, but sometimes you get back behind here some spreading. I'm going to show this by a couple of big arrows back behind here. Some spreading that actually occurs back in a continental mass, an area that normally does not have a lot of spreading. And this minor rifting can develop sags in the continental cratons and masses. And in those sags, you can have significant amounts of sediment being formed. So we think the Bonner quartzite was deposited in one of these continental rift or back, we would call them back arc or intercontinental rift segments that was in the ancient North American craton. And we'll talk a little bit more about this, but ultimately that was uplifted as North America moved on to the west. So if we take a look at more of the specific details of what the belt basin, the location for the formation of the Bonner quartzite might have looked like, I put an expanded view of a simplified view of a depositional environment that you might have seen at the time of the formation of the belt basin. Here we have a big series of mountain ranges off in one direction. The mountains are eroding and sending rivers down the slope and forming lakes, and then out forming deltas. And on the deltas, sand is running down the slope, and into the slope area, sand and shale is deposited, ultimately filling in a basin down below. And here, as I outlined here, you have the shelf sands and muds, much like you would have, say, the modern Mississippi, as it tries to fill in the Gulf of Mexico. Now, I want to point out and want to remind you that the Bonner quartzite and the belt basin formed 1.5 billion years ago. Now, at that time, the world was extremely different. So mountain ranges were still forming, and lakes and rivers and all that were forming. But at that time, at 1.5 billion years ago, there were no land plants. So nothing grew on the surface of the earth, only relatively primitive life in the form of plankton and other types of algae, maybe some other simplified life forms, but all those were in the ocean. There was no land plants, no animals, nothing inhabited the Earth's surface. So that made for a very different world. And in fact, geologists to this day, even us who spend quite a bit of time, really have to stop and carefully think about how things might be different without anything living on the Earth's surface, all of it being in the ocean. Because life itself really can alter the landforms and the way water flows and how sediment is deposited. So a lot of characteristics that we see in modern day Earth, like the bird foot deltas of the Mississippi and other types of formations that exist in modern day continental environments, whether they be areas in around deserts, or around lakes or rivers. Many of those situations were very different 1.5 billion years ago. And instead of features that we would recognize today as being common lake and river and beach type characteristics, it was more likely that characteristics of sediment deposition called sheet flow, I'll bracket this here, where sand has a tendency to flow down the surface of mountain ranges and foothills, not necessarily as focused rivers all the time, but actually as broad sheets of sand, because there's nothing on the Earth's surface, no plants on the Earth's surface, that's trying to constrict the flow of the water as it goes from high to low topography. So many of these sheet flows would have produced really otherworldly looking areas of broad sand coming down from mountains with no plants on them onto shallow plains with no plants, and it would have been a very different look. Areas of sand flowing as broad sheets, maybe hundreds of kilometers wide. it's extremely difficult for us to even imagine what that would look like. It would not contain a lot of the areas here I show in this upper left-hand diagram where the characteristics of the um, river flowing down from the mountain might have a oxbow and meandering characteristics, or where the lake might be constrained by vegetation. A lot of those things would be very different when the Bonner Quartzite was forming 1.5 million years ago. So when I tried to come up with some pictures of what the Bonner Quartzite depositional environment might have looked like at the time, it's really hard because we have life is everywhere on the surface of the Earth now, just about everywhere. So you really got to look in some pretty extreme places where land plants do not predominate to come up with any compatible analogs. Here is a Precambrian artistic rendition of what the Precambrian might have looked like. Precambrian, again, being a period of time older than roughly about 620 million years, where there was not much life on the Earth and certainly no land plants. And so here's a rendition where our moon is very prominent in the sky, which, by the way, the moon was a lot closer to the Earth in those days. The moon is slowly moving away from the Earth. So 1.5 billion years ago, the moon would have been much more prominent. You might have seen some very primitive algal mats down here, things that we call stromatolites, which you might have been exposed at low tide. But you can see here in the background on these mountains in the background and some of the foothills and the nearby slopes here near the beach, no land plants, nothing there. Very, very, very stark. Here's a picture, the only one I could find of a modern analog fairly close by, of the Great Salt Lake as a potential modern analog just visually. Now, Salt Lake has a huge amount of life on its shores and the mountains, but here from this vantage, this one particular vantage, you can see the relatively stark mountains behind the Great Salt Lake, not much on this little piece of beach in front of it. Of course, the salt in the Great Salt Lake doesn't encourage as much plant life as you might normally see elsewhere, and the rather dry environment also limits modern day plant growth. But if there's a modern day analog that might look anything like where the Bonner Formation formed 1.5 years ago, it might be on the edges of the Great Salt Lake. Now, let's spend a little bit of time taking a look at what kind of interesting characteristics you find in the Bonner Quartzite. Because remember, the Bonner Quartzite was just a sandstone deposited in this basin in western Montana about 1.5 billion years ago. So here I put on here a classic slide that talks a lot about shallow water depositions when you have sand flowing into a fairly shallow basin. And there's a lot of information on this slide, so study it at your leisure. But the fun thing I think about this slide is showing some pictures of what the rock looks like. Old sandstones and quartzite look like when they get excavated, and you can see them in here in the upper left. You can see the ripple marks of an old shallow water feature sometime in the distant past. If you take a cross section across this on one of these blocks of quartzite, you can see little ripples and forming where the dark area is probably more muddy and the lighter area is probably more sandy, but you see the little rippled surface, the wave action still being preserved in the rock type. And here now on another piece of quartzite down below here, you can see with the pencils on both the lower two slides giving a sense of scale, the idea of what these sedimentary characteristics are still present in these very ancient rocks, which have gone under a lot of burial and temperature, fusing those grains together like we talked about, but still the depositional characteristics of the sediment are still present. On the right is a big table that barely scratches the surface of what a lot of sedimentologists love to talk about, which is all these different little characteristics, all the way from sedimentary structures that form by gravel, all the way down to plain laminated silts and clays, which might be very, very thin and extend over hundreds of miles as individual thin, less than an inch size sheets, and all sorts of different other characteristics of sand and shale as it's forming and being deposited. And the thing to point here is that a lot of this is simply being produced by the energy that the grains are being moved by the water, the tides, the wind, and waves crashing to produce these various types. So I'll let you take a look at this at your leisure, but you can get an idea of what the sedimentary structures are by the sediment type, a little bit of a description, the specific deposition process, and then what environment. Our Bonner quartzite has pretty much all of these. Now it's mostly sand. So and sand implies that it was worked by a fair amount of energy because all the little fine particles, the shaly particles got winnowed out by that high energy. So it's left behind mostly coarse sand. So most of the sedimentary structures would be affiliated with coarser sandstone environments. But by the way, you can see here where it says, here it is, sheet flow, transport, and deposition. Remember that sheet flow or sheet flood transport is one of the common characteristics we think that was part of the Precambrian 1.5 billion years ago when the Bonner quartzite was formed because of the lack of land plants. So here are a couple of pieces of Carl Nelson's Macquarie quartzite blocks where I've tried to show some of the characteristics that we just looked at in the previous slide. Here's a picture from a piece that Jeremy was working. You can see the very distinct layers here, very thin, consistently across the whole rock, maybe related to sheet flow bedding. Very thin. Many of these layers are less than a millimeter thick. It gives the rock, I think, a very calming element to it because the individual rock layers are consistent all the way across the stone with a little bit of later fracturing here that you can see on a diagonal. Here on a piece that I was working shows a little bit of the foreset bedding, one of the bedding characteristics here. You can see this very linear piece here, but you can see above a little bit of a dip in individual darker elements here where the sand would have come over a little ridge and formed these little thickening foreset beds. So this foreset bedding is a characteristic of shallow water deposition and is prevalent in many pieces of the Bonner quartzite, our Montana quartzite. So if we look at the formation environment from a map view, here I found a nice little picture of what ancient North America would have looked like about the same time as the Bonner quartzite was forming in the Belt Basin. And here we have a picture of North America where it's a zoom in, so all the rest of the continent's kind of difficult to perceive, but I wanted to point out that the person who did this mapping did a wonderful reconstruction job. And you can see outlined here the Canadian provinces up here, and then the states down below here. And here you can see the outline of Montana. I'll just draw it here. And then here's Idaho. And just like this author has done in the reconstruction, he's showing that the western side of these states here sits on the edge of this marine embayment, which we would call the Belt Basin embayment. And in this Belt Basin embayment, a lot of sediment was pouring off of the ancient North American craton from east to west and filling in the Belt Basin. And as we saw, at least 25,000 feet of sediment accumulated in this Belt Basin, all the way into British Columbia, and specifically in our northern Idaho, Montana region. In Canada, it's referred to as the Purcell Basin, but it's the same basin forming the famous Belt Basin, very thick stratigraphy. Now, a little bit about the Belt Basin. There's real questions about where North America exactly was 1.5 billion years ago. And if we're seeing the east side of the Belt Basin, the piece here that includes Montana and Idaho filling in this big open marine inlet, what happened to the west side of the basin? Well, some people think it actually was Siberia, and that 1.5 billion years ago, this piece of what's called the Siberian platform or craton actually was abutting to the North American craton or continental mass, and that between them lay the Belt Basin. And this Belt Basin was being filled in strongly from the North American side, but it would have had some fill in from the Siberian west side. But frankly, we don't see this piece. So is this piece really where Siberia is now? Well, not that much field work has been done on old rock in Siberia, especially up in this area where the Belt Basin material would be. So it could be a while before we end up finding a lot of confirmation about whether or not the other side of the Belt Basin is in northern Siberia. But that's what many authors, many geologists think it might very be possible. So, are there modern analogs today where thick sections of sediment are accumulating that might ultimately form something like the Bonner Quartzite? Well, here I've shown a map of sedimentary environments in the world today, and I've showed here on three stars area where significant sedimentary rock is accumulating. And they're likely candidates. Area just north and south of the Himalayas, the Himalayan mountains producing a huge amount of sediment every year. To the east side, from a cratonic standpoint, of the Andes, where in the upper Amazon basin, thick sedimentary sections are accumulating. And still in North America today, on the east side of the Rockies, particularly, there's large amounts of sedimentary section being accumulated within the North American craton. So these places would be three spots where intercratonic basins are forming, where thick sections of sediment might be deposited or are being deposited, which ultimately could lead to burial, pressure formation, and temperature increases, and the formation of thick quartzites. So likely spots of something like the sedimentary environment of the Belt Basin, although nothing nearly as large as the Belt Basin or as thick as the sections we observed in the Belt Basin back 1.5 billion years ago. Well, we always close out our presentations on the geology of sculpting stone by taking a look at art and architecture. If we take a look at art and talk about quartzite in general, it's really hard to beat the ancient Egyptians, probably the greatest quartzite artists of all time. The ancient kingdoms, particularly the Middle Kingdom, has produced some of the most remarkable, I think, remarkable quartzite figurative sculpture I've ever seen. And if you understand that they use very primitive chisels and hand polishing techniques with different types of abrasives, it's even more remarkable. It's really hard to beat the beauty of the sculpture in quartzite of the ancient Egyptians. Here I put a few more pictures, including some remarkable pictures of some quartzite sculptures. The princess, one of the daughters of Akhenaten. It still amazes me that this is actually made out of quartzite. And then a statue of a court official. The ancient Egyptians, across all three of the major kingdoms, created some remarkable pieces in quartzite, which is quite prominent in ancient Egypt, particularly Eastern Egypt. And some people think that it may have been the prevalence of quartzite in ancient Egypt and the lack of a lot of high quality accessible marble that made them turn to this stone as their choice for sculpting. Somewhat more recently than ancient Egyptian times, last year, Carl Nelson brought back some Montana quartzite for us to kick around with. He generously handed out several large pieces to some of us to take a run at. We're still working it, many of us. It's a hard stone, most of us using diamond tools. However, it does polish nicely, as you can see here in this piece in the lower right. Now, what about architecture? Well, quartzite has been used for complete buildings as well as veneer stone. Here is a picture of the Blue Mosque in Istanbul in Turkey, completed in 1616. And although difficult to quarry back in, particularly in those days, its durability and if you could find the right of, in this case, its blue color, makes it a very attractive veneer stone for one of the world's most famous mosques. Additionally, in the Midwest area, Montana quartzite was used as a key building stone and a veneer stone throughout the Midwest during the 19th century and into the 20th century. Here's a couple examples of two buildings in Sioux City, South Dakota, which I think were particularly notable. One, the more Beaux-Arts upper left-hand building with its archways and ornate windows and frames. I think the quartzite serves it well, and Lord knows that sucker's going to be there forever. And here now, and also in the bottom right, the Andrew Kuhn building with a more simplified modernist look. It also, I think, lends itself well to more of a simple neoclassical frame. Even in modern architecture, quartzite can add quite a bit of character to a building. Here is a modern building from Cologne, Germany, just a few years old, and the thin blocks of quartzite, which have been put on as a veneer to this very strongly geometric building, I think add both the character of contrast between the vertical windows and doors, but also I think the variations in colors, a little darkness and lightness, add a sense of warmth to a building that if it had been done in concrete or in beige colors would have been missing. So in this case, I think quartzite, besides being extremely durable stone, also is a very attractive stone, even in modern architecture. So in conclusion, what can we say about Montana Bonner quartzite and quartzite in general? Well, it's not a common stone worked by the NWSSA, partly because we do not have a lot of quartzite immediately in the Western Washington area, but also because it's a tough stone. It's a hard stone to work, difficult certainly with hand tools, but even with diamond tools, it can offer quite a challenge. On the positive side, however, it is an extremely durable stone, so it makes it perfect for an outdoor sculpture. And if you do simple geometric forms, you can form it into many shapes that are quite attractive. The earth and red color of the Bonner Montana quartzite, I think, is particularly attractive, especially when polished. And although it may not be a common stone for the NWSSA to use, it has a strong historic trend. And anytime you can associate one of your sculptures to the great work of ancient Egypt, then I think you can't go wrong. So here's the end of another Geology of Sculpting Stone, Montana Quartzite. I hope you enjoyed this one. Look forward to speaking with you again soon.